models of interest. And the primary motivation is I study non-convex optimization, and I'm always interested in the kinds of mathematical structure that your objective functions or your parameter space may have that allows us to talk about essentially polynomial time tractable non-convex optimizations. So it's clearly a subclass. And the view of that subclass today will be kind of this geometric view. What this talk is not about, in case, I don't know how many of you are familiar with the popular non-convex optimization I come from the area of machine learning. There, the non-convex optimization that is popular is at that time, where people study neural networks and whatnot. There is some interesting stuff related to this, non-commutative analysis that can be said in that space, but clearly that is outside of that. But in case you're interested to see where the state-of-the-art kind of non-convex results for things like neural networks and other functional approximators lie, there's a separate world out there. I'm not going to talk about that, but just telling you that in case I'm highly interested in that area also, in case anybody wants to talk about that stuff. What I'm going to talk about today is trying in the pursuit of global optimality via geometry. And maybe even forget global optimality for a moment and just think about some use of geometry in optimization. And what do I mean by geometry? Of course, it's a vague word, and for different people it means different things. So one is the classical geometry, vector spaces or more specialized convex sets like in SDPs and whatnot. Other kinds of geometries that we study may involve manifolds, Riemannian and non-Riemannian manifolds and whatnot. And beyond that, if you want to kind of leave the language of manifolds, you can still have fairly structured metric spaces that may arise in your optimization, and you may care about those. For instance, currently very popular, thanks to optimal transport, the Wasserstein spaces, which is a nice metric space. And my focus today is mostly related to manifolds, and that too, a very simple, simple is an overloaded word, simple looking manifolds which support very beautiful geometric structure valuable for optimization. That's kind of what I'm going to focus on. And like high level motivation, this is not 100% true, right? But it's just hand-wavy motivation that, of course, we know that in general non-convex problems are intractable, including one-dimensional ones, including detecting whether you are at a local optimum can be pretty hard too. But nature makes an exception for convex problems because essentially local equal to global happens. The rhetoric question here is, are morally, so read this question as, are morally convex functions the only exception? Of course, a fortiori, literally taken, this is not true, right? We have stuff that happens in combinatorial optimization, etc. But there's also some, but this is a rhetoric question because even there is some hidden notion of convexity. But let's say the world of continuous language, it's kind of a, being able to optimize, or the property of local optimum being global, that's actually a topological property. It's kind of a general property, right? It's sort of independent of some extraneous geometric structure that you have placed on it. But the motivation here, why I'm looking at manifolds, the following. Very informally. So if you're on a nice set, A, let's say some kind of bounded compact nice set, and if your function satisfies this property on this set, that local minimum is global minimum, actually slightly stricter than that, sorry. Any critical point corresponds to local minimum, there's no sadness here, and it's a global optimum, then you can reparameterize the parameter space so that your function appears to be geodesically convex. So you can endow such a function, such a parameter space with the structure of a Riemannian geometry. Under those geodesics, your function will appear convex. This is just an existence result to motivate that, in some sense, if you have a nice local is equal to global property, there's a nice change of coordinates which reveals to you some kind of hidden convexity. There's just a motivation, okay? There's no construction here. It's just an existence result.
Historically, roughly speaking, that's Morse theory.
Yes.
So
Yeah.
it goes back to Morse.
The interesting thing is you have to construct geodesic convexity. Morse theory, I guess, stresses more on.
Yeah, it just does a transformation.
Yeah.
Doesn't care about
The proof of this goes by looking at the quadratic form and counting its singularities. Okay, so the idea of geodesic convexity is actually an ancient idea in mathematics. So let's just revisit that idea. So geodesic convexity was actually originally studied by Carl Menger in his PhD thesis in 1918, following upon Maurice Fréchet, who introduced the notion of metric spaces. And later on, it has been studied in mathematics by various people for various reasons, for studying topological problems in differential geometry. We are not going to go there. My motivation, just to tell you this, it has a long and distinguished history for those who care about that side of the geometry. And within optimization, Tamas Rapsak and then Konstantin Utriste, these guys, they studied geodesic convexity within optimization also a few decades ago. And so here's the simple idea. So if you are in a linear space, convexity is just, you join 2 points with a straight line. Your function anywhere along that line is upper bounded by the average along the endpoints. So if the line is a straight point, you get your convexity in ordinary vector space. And of course, given that picture, anybody would say, fine, if I replace that line with a curve, which happens to be, say, geodesic, and you have the same inequality, you construct a theory of curved convexity. And this can happen outside of manifolds also. There are very interesting metric spaces that people study where you get geodesic convexity. So for us, for an optimization viewpoint, the valuable thing is, because of this inequality, local optimum will be global optimum. That's what I care for. And like any other such definition, it could be a tautological definition if you don't have a way to recognize this property or to construct this property, right? For ordinary convexity, you have full calculus, addition and of course no subtraction, but whatever, conic combinations, project, you have a full way to construct convex functions out of simpler functions. Somewhat similar things, of course, one can do here, but it gets a little trickier. So I want to focus on one very particular class of geodesically convex problems. My favorite class is motivated by just actually this trivial change of coordinates that you may see for scalars. So suppose x is a positive number, so log of 1 plus x is concave in the usual sense. But if that means if you look along lines, but if you recognize, oh, it's a positive number, so I could write it as e to the u or something like that. But along that curve, x to the 1 minus t, y to the t, it satisfies this convexity property. So under the right set of coordinates, something that looks concave in the usual coordinates looks convex. So this is at the heart of sub-area in optimization called geometric programming. So there the word geometry means something else. It means the geometric mean here. For me, the whole stuff gets more interesting here. So under one of the most popular Riemannian metrics that people study on space of positive definite matrices, so they are strictly positive definite matrices. One of the most popular Riemannian metrics on this, I'll maybe just write it down in case you've never seen it before, is at a point x, don't have time to talk about all the stories about that, but it's a nice invariant, kind of bi-invariant Riemannian metric. Under that, that's one of the most standard geometries people study, Riemannian geometries people place on positive definite matrices. By the way, this is the second derivative of the log determinant barrier function, which so is a beautiful connection to interior point theory in case you get. So under that geometry, we get this closed form, beautiful closed form geodesic. This thing is also known as the matrix geometric mean, and it has, of course, that beautiful form because we are in the right workshop for that form because of non-commutativity. And that's the reason I find it really interesting. And functions which satisfy along that curve, this convexity inequality, I call them geodesically convex on that manifold. That's the one I'm going to care about, okay? Mostly I'm going to show you some examples now, and after that I will mention some initial theoretical results and mention a bunch of open problems for, in case you're interested. So here are some interesting examples from the land of STPs and linear matrix inequalities. Condition number of a positive definite matrix, this ratio of lambda max to lambda min. It's well known to be Euclidean quasi-convex, but it happens to be in fact geodesically log convex. An interesting observation. A more challenging one, this comes up in control theory. Originally this was proved by Nemirovsky and Nesterov, and then later adapted and extended by Boyd and Algoy. That the generalized eigenvalue is a function of a product of two matrices. That is Euclidean quasi-convex, and it comes up in LMIs. And of course, if it's quasi-convex, you can still do interior point type stuff, I guess. It turns out to be remarkably, this also turns out to be log geodesically convex. It has some consequences, I'm not going to go there, I'm just showing you some examples. Another favorite example of mine is the trace of a power of a matrix. Power can be any real number. That also is log geodesically convex, closer to zero, it still remains geodesically convex. And the proof of this involves just an appeal to, I think, Golden-Thompson plus some other stuff. Yeah.
These are all STP matrices? Like
Declare a matrix to be otherwise, assume it's positive. Okay. And there's a bunch of other theories one can prove. This ties to, sometimes proving these involves appealing to some of Lieb's results, or sometimes it involves creating new results in the same category as and whatnot, but there's just some motivating examples. Let's, all of these examples can actually be captured by more general theory. So we developed this theory over past many years, which creates a bunch of tools from matrix theory to construct, recognize, mostly to construct geodesically convex functions. And some of the corollaries of those are results like this function. I'm going to talk about this soon. Log that of that. X is the variable. B is a positive definite matrix. AIs are complex matrices. So this is Hermitian positive definite, and these are complex as long as rank doesn't get lost. So it's a positive linear map inside here. You're fine. More intriguingly, or equally intriguingly, I mean, this is intriguing for various reasons. I mentioned some of those shortly. Probably you already know some of those reasons. I know that Ankit knows those deeply. Even log of the permanent happens to have that geodesic convexity. And in fact, not only the permanent, any generalized matrix function has that nice convexity problem. I've not managed to use it for anything yet, but whatever. Okay. So here are some motivating applications where this geometric view turns out to be interesting / useful. So one is this toy application. This is well studied by people in numerical linear algebra, so I'm not saying I'm doing anything better, but this is just for motivation of potential benefits of thinking geometrically when doing optimization. So here's a classical question of computing matrix square roots. So that matrix is not PSD, so please forgive me for that. This is deeply studied in Nick Hive's book on functions of matrices. It's kind of a matrix square root is a building block for efficiently computing matrix logarithms also. Anyhow, so here is the problem. Matrix square root, people wanted to turn that into an optimization problem that you can solve using gradient descent, because whatever you want, gradient descent is, at least in machine learning, the most popular method. So you can write it as this optimization problem. M is a PSD matrix, and you want to find a square root. And in fact, they are not imposing any constraint, but actually implicitly what they want is that they want a symmetric square root. So this is really an honest, kind of unique square root there. By solving that problem. And you can do that. You can apply gradient descent, and you can come up with a multiplication-based method only. No inverses required anywhere.
Again, is X positive definite?
M is positive definite, and because we're looking for X squared, you're just looking for X. So X squared will do the job. Oh, you're saying that I'm not looking for a positive definite square root?
Yeah, I'm asking. Yeah, that's what I'm asking. Which class of X's are? Is it really all X's or symmetric X's? Or?
Here it is just all x's, but there is an implicit thing that this should be non-singular also. But that will happen because m is non-singular.
But you said it was unique, so
So now I'm saying the square root, the square root of a positive definite matrix. If you're looking for a symmetric square root, that is a uniquely defined object. But if you just allow anything, then there's a rotational.
I guess but you want it to be positive definite also.
You would want it to be positive definite also. So here, what they're doing is they're just saying x squared.
Yeah.
If you make it symmetric, so
Yeah.
if that x is equal to x transpose is written as an
Sure,
additional
sure.
constraint, then you get
Sure.
x squared as the answer.
Right.
But x itself is whatever.
Okay.
But what I'm saying is I don't like it. So their whole point was to use the machinery of analyzing non-convex matrix factorization and tensor factorization, using that machinery to analyze this non-convex problem and prove that yes, you can solve it if you do gradient descent with step size equal to minus infinity. I'm just kidding. So, well, what I'm saying is this particular view that when I think of square root, actually I remember a geodesic between this geodesic and its midpoint is really the midpoint between the identity matrix and A. I think of square root of A as that object. So I'm considering this problem as I just want to find a midpoint on that particular curve. So for various reasons, this is not a unique formulation, there's a variety of formulations, but that thinking that I want to point to a midpoint, I want a midpoint of a curve. So midpoint of a curve can be thought of as being obtained by minimizing a sum of square distances, where the distance you use is kind of suitable. Because if you're in vector space, if you minimize sum of squares, you get arithmetic average. If you're in Hilbert space. If you're in a curved space, then minimizing sum of squares of the cost function, okay, that corresponds to what is called a geometric average. And for a very carefully chosen function here, many other functions work. Okay, this is not a unique choice. The minimum sum of square guys actually ends up giving you that midpoint. This object itself is very interesting. A general version of this we'll soon see, but this object is a very interesting object because that distance function takes the ratio of the determinant of matrix average to the determinant of the square root of the geometric average. So it's a very interesting distance function. I could, if you are interested in it, I can tell you vastly greater details about that. So in fact, this is an optimization problem which is not over a Riemannian geometry. Okay, it's over some other geometry. It's a very interesting geometry, nevertheless. Yeah.
How does that compare the iteration compared with the classical Newton?
Yeah. So the like I said, don't solve square roots like that. I will show you the plot. Actually, I don't have the plot. So there is a polar factorization based Newton iteration which works better than the classical right way to do it. Geometric way is better, but geometric way is still not the best way to do it. It's just a motivating example to see that geometry can help, but but it's still not the best way because that's being a super important problem. People have spent tons of years trying to do a good job of it. Yeah. Sorry. Go ahead.
Yeah, so I assume this is faster than like taking SVD and taking the square roots of a single value.
Yeah, so that's the reason people invest a lot of time, especially for the positive definite case. Basically, the default you would say is take eigenvector decomposition and then take square root. And what they want is something for which they can worry about condition number, round off everything very carefully, and those things become delicate. And that's why, that's why I said this is a separate topic. Let's not go there. It's not the point here. But it's an awesome topic because you have even closed form approximations based on Pardee and Zolotov, all sorts of numerical linear algebra that solves it. I'm not the one solving it. I'm just showing you the distinction between Euclidean view and a non-Euclidean view. That's the point. So this one, nightmare of textbook linear algebra person who say, "Whoa, you're computing inverses." It's not such a bad thing to always compute inverses. Okay? This thing actually converges linearly, even starting with a singular matrix. It works as fine and beautifully the convergence analysis is just half a page long, and it's not based on Riemannian geometry, it's just based on some other geometry, and the convergence analysis just talks to some nice fixed point theory. But that's not really the point, you know. The point was, did I skip your question?
Oh, so, I think I just missed it. You said it was better than the previous one. Well, what's,
Gradient descent.
yeah,
So
what's better about it?
here it is.
Oh, yeah.
So the blue line is the gradient descent, the red line is my improved version of their method, and the black line is by doing the geometric thing. And the Newton thing that Pablo mentioned would probably come here. So
That converges quadratic.
that converges, well, not globally quadratically, but you see the superlinear convergence very quickly. Yes. So after 3 steps, boom, it gets it. Yeah. But the moral here was that just because you could do it in the Euclidean way and you had a toolbox of mathematical analysis coming from tensor factorization and whatnot to analyze it, doesn't mean it's the way to go after it. Geometry could be better. And if that Newton thing didn't exist, probably this would be the method, the good method, or one of the methods. So that was just, that point. Let's look at this other problem. This is just an interesting math problem that I came across thanks to Ankit's paper at some point. So you may have seen this before. There's this Brascamp-Lieb inequality. And the tightest such inequality, there's a constant here. These are these conditions in there, whatever. So the tightest such inequality, the smallest constant on that side that you can have, yeah.
Sorry, can I just go back one slide and ask just a naive question? Like, why is this method used over like rational approximations? Like rational approximation of the square root converges very quickly, but
Which method is used?
I believe you can efficiently construct rational functions that approximate the square root exponentially well in degree.
Sure. I'm saying this is a full topic, so people, you can follow up on that. There's stuff, other approximations beyond just rational approximations based on nice contour integrals, etc., etc. Numerical linear algebra, people have solved this to death.
I see.
So that's not really the point. The point here is the distinction between the Euclidean view and a non-Euclidean view. That's all.
But I guess maybe my overall question is this the method that's used in practice?
No, of course not.
Oh, okay.
Of course not. That's what I'm saying. This is not the world's best method for square roots, but it's vastly better than just doing dumb Euclidean gradient descent. If you want me to be blunt about it. Okay, so there's this beautiful inequality. The tightest constant there is given by solving this as the infimum of that problem, and that's a really nice optimization problem. I actually saw originally this thing in applications to geometric complexity theory in Ankit and co-authors' work. Probably one of your other co-authors also here I saw.
Yes, Rafael.
Okay. But I know people have studied this a lot through various angles, including uniqueness, etc. It was carefully established by these folks. And then people in convex geometry, they study these Brascamp-Lieb constant and Brascamp-Lieb inequalities, etc., from Riemannian lengths, etc. But so this is once you take logarithms, you want to minimize. This is what the optimization problem looks like. And the cool thing about this optimization problem is, even though it is non-convex in the usual Euclidean view, under this geodesic convexity that I talked about, this problem happens to be strictly geodesically convex, which would also, the strictness would solve this unique solution as reduce, and the G-convexity makes it possible to invoke a variety of optimization algorithms to try to approximately solve it. Still not that easy to solve, but I'll show you a quick 2-line proof. It'll be a little fast, but of this geodesic convexity. So here goes. Recall this is our geodesic, and we just want to prove that I'll just prove it for a single matrix, but multiple matrix case just follows the same way. We just want to show that along that geodesic, that log, that blah, that stuff, this stuff, there'll be just a single x here. There'll be several BIs, but there'll be just a single x, doesn't change anything. But this function is convex along that curve. So here goes, here's the curve. I just write this notation, let this be a positive linear map. Then you can show that the sum of those positive linear maps is upper bounded by, so the positive linear map applied to geodesic is upper bounded by geodesic average of the positive linear maps, and then you apply a concavity property of this. So don't worry if you don't get all the details, I'm just compressing to show you that it's actually easy. The interesting inequality is this one. This is actually Kubo-Ando's famous inequality on sort of the contraction property of positive linear maps along those geodesics. We kind of rediscovered it when we did it, and then somebody wrote to us that, hey, Kubo-Ando did it before you. And now you just take, apply log. Log is monotonic, so you can apply it everywhere. So you get log that of that stuff is less than equal to, I mean, log that is a, determinant is a multiplicative object, and log just, of course, does log. So log applied to this side and this side yields the, I'm just proving midpoint convexity, but the same idea goes for any arbitrary t. So after just 2-3 lines, you can see that, okay, that computation of that Brascamp-Lieb stuff is clearly geodesically convex optimization problem, but of course we proved it with general linear maps, not necessarily just BI star x BI, but it's, yeah. So that's that. Fun generalizations I don't have time to talk about, I just considered for the heck of it, these types of things. I don't know what these objects mean, but in case you care about fun mathematics, this is like some fun stuff I was looking at. If you instead of determinants consider permanents or generalized matrix functions, where generalized matrix function is given by that. So it includes determinants and permanents, a special case. Then, actually the determinant case, the BL case is special, because this general case is not geodesically convex. However, it is a difference of geodesically convex functions. So the numerator is geodesically convex, so is the denominator. So if you take a log, then you get a difference of geodesically convex functions. And the proof is slightly, just as based, the proof is by notation, and I'm not going to go in there, but I just wanted to share a fun random generalization for people who care about permanents. Okay, let's look at some other applications. I guess I'm going a bit slowly, so I may skip a couple of the applications and tell a little bit about theoretical results also. Results related to optimization, not just this convexity. So let's skip the optimal transport result. And maybe, let me skip also the Gaussian mixture models. I have only 45 minutes, right? And then this time is supposed to be for discussion.
A little more.
Okay, so maybe then let me not skip.
One
Because
thing
this is
about
one of my favorite examples.
Wait, mention there has been some interest in transport here, so.
Okay, well the
Previous
transport,
talks,
the optimal transport problem is kind of just pretty simple. There the message is the same thing. It looks Euclidean convex, the one I'm looking at, but that's not the best way to solve it.
Which metric do you use?
Or this is my Riemannian metric.
For the optimal transport.
Because I'm not solving the general optimal transport problem, I was looking at optimal transport between multivariate Gaussians or multivariate elliptical distributions, which kind of end up having similar looking optimal transport. So not general distributions, that's why I kind of skipped it. General distributions require some other stuff. Okay, let's talk about this classical Gaussian mixture model problem. This result does not, I'm not gonna talk about global optimality here, right? It's not globally optimizable in the general case. I'm just going to mention to you how geodesic convexity was exploited here to come up with a nice optimization algorithm. So we are looking at a mixture of Gaussians, and you have training data, and you want estimate of means and covariances. And of course, de facto choice, people study, call it, I guess, the expectation maximization algorithm. In case you haven't heard of it, fine. Keyword suffices, EM. And it's a non-convex problem, and there is, of course, a bunch of theoretical progress in certain cases on that. But practitioners, when they want to fit the parameters of a mixture of Gaussians, they still use EM method. So regardless of other progress. And as you can see, covariance matrices, as long as they're not singular, they fall within our picture of looking at covariance matrices through the lens of Riemannian geometry. So that's what we do. We say, okay, well, let's think of mixture parameter estimation as a geometric optimization problem, rather than going by Cholesky decomposition, which actually numerically sucks, even though it's pretty tempting to always write things as LL transpose. So we do that, and turns out actually EM is great. You know, Riemannian optimization with all this geometry view, etc., it actually sucks compared to the default method. It turns out it's there for a good reason. And we really did, we used this nice toolbox ManOp, which we try to further improve actually to fit our needs. So EM actually works really well. It's hard to be. This is a fairly, I mean, it's not a large problem, but it's still, 200,000 observation in 35 dimensions. And so EM still big. And here, this is the physics level thinking here, that we are trying to solve an optimization problem which somehow ends up being very advantageous to the EM method, and the Riemannian view doesn't end up working that well. And so we revisit the formulation purely intuitively, and I still don't have a deep reason why it happens to work. You'll see soon that it works. So if you look at log likelihood for a single component, so if your Gaussian mixture model just had one Gaussian in it, and you have n observations, this is what your log likelihood looks like. Or sorry, whatever, negative log likelihood, I keep forgetting. I like to think of problems as minimization. So this problem, convex in this. So this is the Euclidean convex problem, but even the single component problem, which actually is a closed form solution by the way, it is not geodesically convex. So somehow, and the single component problem being convex is what EM method dramatically exploits when you implement it. Because it iteratively goes through simplifying its cost function, building upper bounds, and the upper bounds are always convex. And so it truly exploits that single component being Euclidean convex. And it's not geodesically convex. So our physics-based insight was, why not reformulate it in new coordinates so that it becomes geodesically convex. New coordinates happen to be what stats people call like as natural coordinates by lifting it to one more dimension, and then we just work instead of n by n covariance matrix, d by d covariance matrix is d plus 1 by d plus 1, and the reformulated version becomes geodesically convex, single component, but the mixture of course is still overall non-convex. But somehow this reformulation, this change of coordinates seems to probably have a very good effect on numerical conditioning, that's my guess. It actually ends up letting Riemannian optimization soundly outperform. And this is actually just one example, it's across hundreds and hundreds of examples we ran because EM is a famous method, so one has to do more experiments. It actually works quite well. But I still have not fully understood or managed to theoretically explain why that reformulation seems to be helping so much. My guess is some kind of numerical conditioning, because typically when you use a different metric, your numerical conditioning, because you do change of coordinates, numerical conditioning benefits. But still I would love to discover a deeper reason that why this particular change helps us so much.
Can you just show that slide again with the change?
So you just augment by one dimension and you get this matrix. So we estimate this matrix, we keep that coordinate fixed, and we just interpret the stuff as Q.
What's QN?
Oh, it's just a shorthand for this stuff in the coordinates.
Is it easy to write on the board? Or is it
This was like this
scroll
was
it? Oh, QN is down.
QN is one of these guys.
It's one of those guys up there?
Yeah.
Oh, okay.
you seem to be beating EM quite a bit now.
Yeah.
Use this.
So some people have actually now built it into their toolboxes, but there is inertia, right? Because EM works better for other manifolds. This idea seems to so far work the best only for this manifold. But the beauty is once you use optimization, you can discover, I'm not showing those slides here, you can immediately build large-scale stochastic and whatnot versions of this and really, be faster than EM hundreds of times. But somehow the annoying thing is, how does the change of coordinates, how does it so deeply impact the conditioning that you see those speedups that we haven't understood?
Truly, what does EM stand for?
Expectation maximization. Okay, so that was that, and maybe I'll just quickly mention one manifold that is not the positive definite matrices is this classical statistics problem called principal components analysis. You have data and you're looking for the direction in which it's spread the most. So people build a covariance matrix of the data, take its eigenvectors. Largest eigenvector gives this direction of spread, second largest gives that, and so on. So it's a very fundamental technique in data analysis. And the version that we are interested in is that you have very large number of observations. Suppose everything is mean zero, it's pre-centered. So you observe these Zi vectors, lots of them, and this is the sample covariance matrix, Zi transpose. It's given as this summation. Finding its largest eigenvector can be written as this minimization problem, where the minimization is now over a nice manifold, it's just a sphere. So what we said was, well, let's look at this large problem, and we revisited, there's a lot of recent work in Euclidean optimization, both in machine learning and GCS communities, that when n is large, so your covariance matrix, but it has a very special structure, right? It is a summation. Can you exploit that summation structure to deal with very large values of n efficiently? And it's a non-convex problem, but we know we can solve for eigenvectors, this kind of hidden convexity structure maybe. So can we do that using a method which does not need to use all n observations at each iteration? So that's like a stochastic gradient type method. But if you can do that, you can solve this non-convex problem, and you can do a bunch of analysis if you do the Euclidean analysis. But again, a very interesting property happens, that even though this problem is non-convex, and of course a sphere being a compact manifold does not support global convexity structure, what happens is for this particular eigenvector-like problem, it satisfies some convexity-like property. That convexity-like property is called so-called Polyak-Loyasevic condition, but I'm not going to go into that, but just saying, even though it is non-convex, certain non-convex problems satisfy an inequality which describes how fast the cost function grows in terms of its gradients, and if that property holds, then we can actually design efficient optimization methods for them. So this property was originally studied in differential geometry, then came into optimization where people forgot the differential geometry connection, but it turns out that for this geometry, we could show that even though this is a non-convex problem, it satisfies this hidden convexity-like property, as a result of which you have half-page analysis of why you can have a method that converges at a linear rate to the optimal solution. So it's not 100% precise what I'm saying, because there is some language of probability involved in these statements. So, yeah.
So I'm trying to understand why the geodesics help on the sphere. Can you give some intuition to that? Because it would seem to me like, in the sphere there's kind of one direction in the direction that you're already in, and there's n-1 other directions, and which all kind of look the same. So it seems like most of the directions
Maybe
all look the same, right? So where does the geodesic help you?
So there are two things here. The geodesic is actually helping in a very mundane way. this is a non-linearly constrained problem.
Yeah.
By remaining on geodesics, I'm just satisfying my constraints at all points.
Yeah.
That's
although
how
I
it
think-
is. I'm not using it in a more dramatic version.
Yeah.
The more dramatic property that is happening is, there's also a cost function here. The
Yeah.
cost function along those geodesic ends up having this convexity-like property.
Yeah.
So that's the more valuable property where geodesics are implicitly happening. So it does not have that convexity-like property along arbitrary lines.
Yeah.
Only along those curves it has this convexity-like property, which allows you to exploit it to build fast algorithms.
And does the algorithm, is it different just doing regular gradient descent and then renormalizing all the time?
Beautifully, it turns out. So this is actually stochastic, so not
Or, yeah,
regulation.
regular
So the
SG.
B flies in stochastic, but yes, it is no different from doing a stochastic power iteration.
Okay.
It's just a Riemannian geometry explanation in few lines
Sure.
of why stochastic power iteration works.
Great.
So, okay, I think this was the summary, some blah blah summary. Let me just quickly tell you about some theory. But I went too slow. We'll just mention a couple of highlights and then just wrap up, and leave the slides there for discussion in case needed. So, for first order convex optimization, for first order optimization. So, what do I mean by first order optimization? I'm going to consider the class of optimization algorithms that seek to minimize f of x, and these are iterative methods. So they run for k iterations. At each iteration, your method is allowed to compute f of x and a gradient of f of x. And using these two subroutines, you want to basically now say how fast does my method converge to an optimum, either to a global optimum or to a stationary point if the problem happens to be kind of non-convex. And we assume that the cost function and the gradients are either exact or we have unbiased estimates of those. So gradient descent runs this iteration, and on manifolds you just run a version of it which pulls it back along that geodesic onto the manifold. So don't need to worry about details, just saying that the iteration involves this non-linear map which keeps stuff on the manifold. And we wanted to analyze first order methods, and many of them look like this. How fast do they converge? That's where computational complexity theory and optimization have had some of the greatest successes in complete theory of first order optimization in vector space. So our aim is to look at G-convex, and for Euclidean case, there's a bunch of theory that exists, starting with seminal work of Nesterov and Newton, and then many more. But for geodesically convex optimization, such a theory was absent and still is in its infancy. And I'll mention to you now. So, I'll mention to you that we can actually, for geodesically convex problems, parallel some of the first order theory that exists for Euclidean convexity. But interestingly, not that surprising, but interestingly, the curvature of your manifold will play a role in how fast you can optimize. And here is where curvature comes in for us. So if you're analyzing this Euclidean gradient descent iteration, that's what the iteration looks like. And high school trigonometry is used here, which says xt was so far to the optimum x star, and xt plus 1 is so far, and this is the distance between xt plus 1 and xt, which are constructed like this. So you end up looking at a triangle, and you want to control essentially how far is xt plus 1 to x star. So of course you have to do some trigonometry on that triangle, and that is done by just using this law of cosines. You plug this stuff in, and then the effort lies in essentially controlling the third term somehow. But point is, this simple law of cosines, which we don't give second thought to, ends up getting used. Now in curved space, you don't have straight lines, you have these curved lines, but you have a similar triangle. But we don't have a law of cosines. There exists something in hyperbolic space called hyperbolic law of cosines or law of hyperbolic cosines that looks like that. It's not quite of the same form. it's not so usable because we want to relate A to B and C in terms of this angle gradient. So after doing some work using some comparison theorem from differential geometry and differential equations, you can actually prove not an equality but an inequality, that the distance A square is upper bounded by that, and there's this distortion term which captures the effect of curvature. So if kappa min is a lower bound on the curvature, so people study in differential geometry optimal transport often spaces with lower bounded curvature. So if suppose this kappa was 0, then this zeta becomes equal to 1. So even though we weaken, at least we recover the same Euclidean picture. Otherwise you suffer that distortion due to curvature. And of course, the bigger that number is, the more kind of stretched out the triangles are, the more you'll suffer due to curvature. And so we get this curvature inequality. Turns out, this again we kind of rediscovered. People in differential geometry in I think about 2001 had discovered this inequality, but actually our proof holds outside of Riemannian manifolds also, but that's a side remark. So once you have this triangle inequality, you can actually extend those Euclidean analyses and say that, well, in Euclidean case, after t steps, you are within this of the optimum. In the geodesically convex case, you get exactly matching results, but distorted by curvature. And I think what I'll do is,
What's D? What's capital D there?
sorry, this one?
Yeah.
Oh, this is this is a good cat. It's bound on the diameter of the domain that you're optimizing over.
So in the previous slide, I was kind of thinking of B as like a little bitty step size, right? Is that wrong?
No, so
D is like your total remaining distance to the target?
because we always involve x0 to x star,
Okay.
because there is that starting from
Got
x0
it.
to x star, so you kind of have to control how big that distance is.
Okay.
So that pops.
Does that assume positive curvature or negative curvature?
Negative curvature. So in positive curvature, you can actually this in positive curvature you'll still have this inequality, but this bound will be less than or equal to 1, so you actually get still useful inequality. But global results we only have those in negative curvature because geodesic convexity exists globally only on non-compact manifolds like negatively global. So anyhow, let me skip this, but mention to you the cool thing. So in gradient descent methods, one of the most famous methods within optimization is Nesterov's accelerated gradient method. So there's a lower bound on how fast can you optimize if you only have access to function values and gradients. And the lower bound says if your function is convex but its gradient is say Lipschitz continuous, then after k steps you're within a factor of 1 by k square, 1 divided by k square of the optimal, and this you can do better than this. So this is the lower bound. Whereas the gradient descent algorithm, for that you can only guarantee that it converges as 1 by k. So there's a gap between those two, and it was an impressive achievement in optimization when Nesterov discovered an algorithm that closes the gap. So that's what the accelerated gradient method stands for, which matches the lower bound of how fast you can optimize using first order oracles. And given the story so far, thinking that okay, curvature just pops up, that fine, we'll be using curvature, we'll be able to generalize even that method into the case of curved space. But it turns out we cannot so far. We could not. We could only prove that locally around the optimum, we can show that we can discover an accelerated Riemannian gradient method, but globally we could not prove. And that was just a teaser picture. I didn't want to talk about that. So we actually end up showing, for G-convex, blah blah blah. If you're close enough to the optimum, then you can converge at the theoretically optimal rate. But the open problems we required the function to be not only geodesically convex, we required it to be strongly geodesically convex. This is a local result. Can one make it global, that is get rid of this thing? And a much more dramatic question is to study, develop lower bounds on how fast can we optimize based on curvature. Like there are some bounds where curvature pops up in the bound, but is that the right dependence? How does curvature truly optimize? What is the kind of lower bound depending on curvature? Because of course, a fortiori, all Euclidean bounds also apply here, but we want to say, how does curvature come in? So those are the main open questions for understanding first order Riemannian optimization. I'm completely out of time to talk about the other open problems in the area, but I think I will stop here now. Thanks.
Questions? So one nice kind of gradient descent is the Frank-Wolf or projected gradient descent, which keeps things sparse.
Yeah.
Oh, wow.
So I wrote recently a paper on Riemannian version of Frank-Wolf also. It's not as general as what you had in mind.
Wow.
It has a caveat. But this is like all the problems so far, they didn't have constraints.
Mhm.
The only constraint was the manifold itself. But if you have additional constraints, then we try to develop Riemannian Frank-Wolf methods, but this applies only to limited class of problems so far, because you need to solve non-convex subproblems. Sometimes those non-convex subproblems are solvable, not always.
Yeah.
Yeah. Okay.
What's your next slide?
Ask the question.
Questions? Thank the speaker again.
We reconvene at 11:30. Get someone else to do this.
I wasn't here most of this.
Yeah, they provide. Just kidding. I knew there was a break, but I didn't remember.
Yeah.
Question about your marriage.
He didn't even know what topic it stopped.
It's like my